And then I'll start. So schedule for today. So this is all posted on the website. If you guys have the Wi-Fi access, you'll be able to see this anytime you want. But our schedule for today looks like this. You'll see a bunch of good talks throughout the day. We also have a poster session this afternoon. For all of you that have posters, and if you have them with you at the moment, there's a storage place out in the lobby for those posters. So you can easily take them out there. You'll see a bunch underneath the stairs. Feel free to put all your posters there for now. And we'll give you some updates right before the lunch break on how to get those set up. We're trying to figure out the best plan for you guys getting your posters on their easels.
Yeah, so the poster session is going to be upstairs, and we'll put them up in the afternoon break. There are going to be 2 poster prizes available, which are going to be sponsored by Farm Etc. Finally, the code of conduct is very important and is available on the website if anyone wants to read it in more fine detail, but please just be respectful of the building. To everyone here, this holds true to all the social events and all the scientific sessions as well. So please have a look if there is any doubt. The social media, if anyone still uses Twitter, there's a hashtag. We also have Slack. If anyone wants to join, there is a link on the Alchemistry website. And yeah, it's a nice way to.
So finally, we want to thank each and every one of you. We know how hard it's been over the last couple of years, and I'm glad that everybody that's in this room was able to stick through it and join us here finally for this event. It's hopefully take full advantage of it. You have a bunch of free energy experts in the room. Feel free to collaborate, talk, chat, whatever you guys want to do. That's what we're here for. That's what we bring this community together for. So we look forward to spending the next 3 days with all of you. And yeah, thanks again. I think we can get started. So we're going to have our first session chair introduce our speakers, and that's going to be David Hutton.
All right, thank you. Yep, so welcome everyone to the first session. I believe this session is especially in honor of 10 years of the conference, and the organizers have actually thrown in a bonus 3 years as well for free, so that's great. So our first speaker today is going to be Michael Schertz from University of Colorado, Boulder, and he's going to be talking about free energies, what we've learned about how to estimate them. So take it away, Michael.
All right, can everyone hear me? All right, is it coming through the microphone? Okay, cool. Great, well, so it's great to be back here. 10 plus 3 years since the first meeting. There were about 65 attendees that we had to sort of rustle up the first time, and about 24 industry. This time, 170 attendees, about 270 applied. The industry is, I thought it was higher. I guess it's more like 40%. I was hoping it was above 50%, but there's definitely more being involved. Also, almost everyone is at different places than they were then, I've noticed. Virtually all the affiliations have changed, maybe 80%, 90% turnover. Also, somewhat longer ago, I was born 2 miles away. So, that was more than 13 years ago. So it's fun coming back to Boston. So acknowledgements I want to start out with. 2 people particularly in my group who've done a lot of the work I talked about, Himanshu Palawal and Levi Naden, and a lot of external collaborators, especially on getting MBAR, the code up and working, and funding from NSF. So what have we learned about estimating free energies since then? So some topics I'll cover. MBAR is reweighting from the mixture distribution. I think this is an important conceptual way to think about it that helped me a lot to help it all fit together and make it simpler. Histograms are unphysical beasties best avoided if you can. Nature does not bin, generally. Fun things you can do with reweighting from different distributions, tricks we've learned in the past, and mapping between distributions and extensions to ML. This will be more sort of view towards the future as we have not done. We're still working on some of these. There's not really much to present on there. So one thing that I want to sort of present some context for is this idea of importance sampling. It can save us from having to do configurational sampling. If you have some integral, a weighted integral, so that P of I is some probability distribution, so you're computing these weighted averages, what you can do, as you always do in math, is you multiply by 1, right? So I'm multiplying here by 1, but it's a special one. I have some other probability distribution, Pj. And if I just rearrange this, then I've got this ratio here I'm multiplying by this new distribution, PJ, not the one I'm interested in averaging over. And what we can do is replace this integral with Monte Carlo integration. We take samples, and this is the key, we take samples from this distribution, PJ, and if we multiply it by this weighting factor, this ratio of the two probability distributions, then we can calculate observables from one distribution, but doing our sampling from another distribution that might be cheaper or easier to calculate. Notice I haven't put any like energies or anything in physics now. This is just statistics. And if this ratio is similar in magnitude, as this varies, we can avoid regenerating data. We regenerate from this distribution, we don't have to regenerate it. Because if you're doing any sort of configurational sampling with a complex physical system, it takes a really long time to decorrelate your sampling. One fundamental lesson we've learned in the last 10 years, you want to put the statistics back in statistical mechanics. A lot of the ideas that have been developed in statistics and maybe languished a little because they didn't have great applications, but there's a lot of really good applications for them in the statistical mechanics. That's something that we should keep doing more. So for physical problems, we do know these distributions. Now let's put some physics in. And we can do important sampling with this. We're interested in Boltzmann distributions, where the probability is proportional to temperature factor times an energy. And so this is an important, I think students like lose track of this a lot, is that the Boltzmann distribution is a proportionality. The energy is proportional to beta times ui. Really what it equals is the Boltzmann factor divided by the partition function. And this, I like to think of it more like this. This is the probability distribution that we're sampling from. And I always think works better if you work with explicitly put in the normalized distributions to begin with. A lot of the formulas, you lose track if you forget to always include the normalization here. So this is how I like to play with things when I'm trying to work ideas out. And so for this ratio that we need to do important sampling just looks like e to the beta free energy difference between the two distributions minus the potential energy distribution at a given x. So this is the factor that keeps coming up when we want to do important sampling. So this is one thing that I found a fundamental lesson. Proofs and equations are always easier to work with as probability distributions, especially as normalized probability distributions, not energies. One example is probabilities add when you are summing events. Energies don't. You have to exponentiate and then add, take logarithms. It gets really messy. But that's one example of why probability distributions, if you're trying to work out the theory, are easier to work with and easier to see what's going on. So it gives us some familiar formulas. Here's our ratio of probabilities that we need for importance sampling. So if I take that and plug that into calculating the averages, what if I just plug in 1 here? So I turn this into just a normalization check. If I plug in 1 to this, then I immediately get out. I can take this constant over to the other side. The Zwanzig, FEP, whatever you want to call it, that fundamental relationship of computing free energies between two states when you're only sampling one. And again, this is sampled from one of the distributions. It's the delta energy difference to the other. And so one fun thing that is important, that is useful. The issue with this is that ratio, if that ratio doesn't stay roughly close to 1, within a couple of orders of magnitude, you get really bad convergence. What frequently happens is one of those ratios dominates the entire sum. The rest are nearly 0. One is big, and you don't have reweighting from all the samples. You have reweighting from one sample, which is not going to be very good. And so you need to have good coverage. You need to have overlap between your two probability distributions so that ratio stays the same. What if we're interested in calculating free energy as a function of some coordinate, whether it's configurational or whatever, but this is sort of abstract coverage of space. If you're interested in samples from here, like maybe reweight from this distribution, over here you'd reweight from this distribution, but here, is there some way we can benefit from sampling from both distributions? They both cover this area. Can we use them all together? And the answer is what you can do is simply mix the distributions. You take all the samples you carried out from your simulations, dump them in one pot and say, hey, that's a new probability distribution. And as long as they're all normalized, you can just add them up according to how many samples you have. Can you run one simulation to get that distribution? No, but that's okay. You run 5 simulations and you extract the probability distribution from all of them together. Now, what does the potential energy, if you take the logarithm of that distribution, can you get a potential energy out? Yes, you can, and enveloping distribution sampling is essentially that, which will come up next. So this is our mixture distribution. I have to average it because I've got a fifth from these, a fifth from these. That's what it looks like. I can define it with different numbers of samples as well. So that is a distribution that sort of covers the entire space I might be interested in, if I can think clearly enough to put simulations in all the areas that I'm interested in. So there's a mixture distribution. So this multi-state Benedict acceptance ratio, which I did not realize at the time, that was originally drawn together, is that it's important sampling from the mixture distribution. If you look at this equation, it's sort of a mess. This is a set of, this is actually n equations, a set of nonlinear, or k, n is the number of samples, equations, because the free energies appear both in the bottom and oh, that should be a k there. Whoops, that's very important. I'll fix that after. This is a k because we're summing over all of them here. But if you squint at that, you can realize actually this is just the sum of these. That's the mixture distribution. We're just reweighting from the mixture distribution. And conceptually, that's all it is. It's much easier to think about the equations and how it's all set up and how you design new things, new algorithms, if you think about it as reweighting from the mixture distribution. Observables, it's the same thing. Once you calculate these weights, then you can calculate observables at any point that you might want to sample, as long as you have collected some good samples from that. So yeah, the fundamental clarification that we've learned that I think has made things a lot easier to extend. It's just whatever you want to call this equation from a distribution constructed to give overlap, but it's just the statistical idea of importance sampling. Some other useful facts. Reduces to Benedict acceptance ratio. It's numerically exactly the same thing, and algebraically, once you jiggle things around a little for 2 states. You can get it from the weighted histogram analysis method, and the limit of shrinking your histograms to 0 width. Histograms, not great. It's the maximum likelihood estimate of the free energy given the data you've collected so far. Provably the lowest variance reweighting estimator you can derive. Lowest variance unbiased estimator. It does require calculating the ratios of all the probabilities. You need to be able to calculate, if you have a given sample, what its probability would be in all of the distributions you collected, which can be require some overhead. So it is important. The basic formula discovered, though not well characterized by Bartle, well, probably some others before this. Gibbs discovered about 90% of what there was in statistical mechanics. Most of it has been elaborations. If you go in statistics, people had these ideas way before that. So there are very few new ideas. Please check if you think you invented something that was probably already in the literature 20 years ago. You probably have some good ideas to extend it, but look back when you cite things. For important discovery, it's very useful to have an easy-to-say name. So people will use it more if you do that. Important discovery. What's the fundamental difference between WHAM and MBAR or other multi-state reweighting? So you're constructing histograms if you have WHAM, and you would get a density of states, which can be used to compute properties. You can compute an average by multiplying the density of states. This comes back from physical chemistry. Your observable is a function of the energy times your Boltzmann factor. Here it's a beta E, just the energy of that entire level, because you group together all the energies of the level. But all of this multi-state reweighting, what you're doing, you are constructing a density of states, but your density of states is a sum of delta functions. Now, delta functions are horrible for visualizing because higher density just means really closely packed together delta functions, and it's hard to see what's going on. However, it's really good for calculating expectations and doing integrals. If you do an integral of a function with a bunch of delta functions, you just get a sum of things, right? That's what you see in those MBAR equations. You're getting some expectations or sums of things times these weighting factors. So you have your samples. You just have to do a little bit of math to get your weighting factors, and then you can calculate all of your averages at whatever temperature you want to if you've collected the data. There's histogramless approaches have real advantages for things like potentials mean force, because here your free energies are dependent on your bin definitions. Here, there's still binning here for the samples, but there's no binning in calculating the free energies there, and you get many fewer. You don't get these edge effects depending on what the size of your bin is. Yeah. So what useful distributions can we sample from? You can do a temperature scan, a few temperatures, and get properties, essentially continuous properties as a function of temperature. Free energies of binding is, of course, common. You have some coupling parameter going from the ligand being there to the ligand not being there. Potentials of mean force. We have some work on this that I'm not going to talk about. Parameter scans, new model parameters for doing optimizations. There's a lot of things you can do. So, for example, we can use these techniques to scan molecular simulation parameters. Here's some work that Levi did a few years ago. We're looking at Leonard-Jonesium in water, and we want to say, okay, can we figure out the free energy of solvation of essentially all molecularly relevant Leonard-Jones spheres? So we start with just 10 example molecules. But from that, we can calculate the free energy differences for all these other sizes from just these simulations with well-defined error bars. We do this, oh, we didn't get the small ones very well. Great, let's throw in one more sample here, and now we've reduced the error to less than about 0.1 kilocalories per mole over all of these. It was sampling everything from something like United atom methane to a buckyball size sphere. All of that with just about 10 simulations. Or let's get ambitious. How about all possible ions modeled by charged Leonard-Jones spheres? So we're doing sigma, epsilon, and q from -2 to +2. And this is what you get. You can go through. Notice that the error is always within about 0.5 kcals per mole. This is about with. We'll do some clever things to calculate all the states, but it was only about 3,000 CPU hours to look at all of these. Why should I care about this fancy pants calculation? Well, you can test salvation free energy to analytical theories to really an impressive level of detail. For example, what about the difference between explicit salvation, as with tip 3P, and Born salvation theory? Well, if I look at the difference, you can see, because water is polar, you can see the asymmetry between Q is -1.2 and Q is 0.2. You can see the differences between the Born, whether it's above or below. These all have relatively low area. We've not really done this. There's too many other things to do, but I'd love someone to play around with this data set, because we've got this for all these charges, and see, can we come up with better implicit salvation for water matching this data? Which is, once you set up the infrastructure, just took an afternoon on a cluster to generate. It's useful for calculating finite derivative differences, and this is really important, a really important trick here. So if I'm interested in the derivative of the free energy with respect to some parameter, I can do it by a finite difference approximation. If I just run 2 simulations, this is actually, we want A to be as small as possible to get a good derivative, but delta G has noise. If you just run 2 simulations, this does not give you good answers at all because of the statistical noise. You have to collect a huge amount of data. If we look at propagation of variances, if we're interested in the differences in, say, 2 delta Gs, we know it's the variance of the 2 calculations minus the covariance. But I think an important thing is if you calculate these 2 differences from the same data set and reweight to 2 slightly different parameters, MBAR takes this into account. So you can calculate the finite differences with your sampling, and this error goes away. The covariances are all contained, so you get very low error finite difference derivatives. You can essentially go as close as you want to, up to the level of precision of the energies that you collect. So we can do things like rapidly validate simulation parameters for free energies. We run one simulation with a 0.9 nanometer cutoff, and then reevaluate at all those other cutoffs, right? There's not that much of a difference between them. There's very high overlap between these configurations. And so from the energies of MK states evaluated at samples from just K simulations, you can complete the free energy of these and look, scan over 6 different parameters and find out, okay, what's the cheapest parameters that I can get that are statistically identical to, as expensive a calculation as you can do. But you only need one actual simulation, and the rest are energy reevaluations. So we've implemented this with PyMBAR, fast, robust, efficient. includes many examples, salvation for energies, force bias experiments, heat capacity curves as a function of temperature, automated installation through pip and conda, which you can download it here, and then through Git, and then on conda. We released a 4.0 that I think has a lot of improvements that I've been trying to get in for a long time. Built-in bootstrapping of uncertainties, which works better than the evaluations. Improved robustness, JAX CPU, GPU acceleration, improved ways to calculate free energy surfaces. So I think a fundamental finding here, people will cite you if you're at least a good implementation. So that's another thing we've learned over the last 10 years. So if you're still using an older version, a 3.0 version, please upgrade to 4.0 and let me know if there's anything else we can do to improve. So yeah, that's great. How do you do important sampling between distributions that don't overlap? I want to talk a couple minutes about this before finishing. So what if you have truncated harmonic oscillators? So if I collect data, if I collect this sample here, what is the ratio of the probability difference between this distribution and this distribution? Well, it's infinity. There's no phase space overlap. That ratio is either 0 or infinity, depending on which way you do it. I can't calculate, using importance sampling, the free energy difference between these two potentials. There's no way to do it. But what if I construct some function that maps between these two distributions? This function here, so I shift the means and scale based on the force constants. It turns out that if I do that, if I know what these underlying force constants are and what the means are, it exactly maps the distribution. If I reevaluate the energy from here to here, it turns out the energy difference is 0. It's the exact same energy. The analytical free energy differences are the logarithm of the ratio of these force constants. There should be something we can work with here, right? And so if the Jacobian of this transformation is this ratio, we should be able to do something here. And it turns out you can. You can apply this coordinate mapping. The free energy difference is the same average we've been looking at, but you have to add in a Jacobian term. This is the MBAR version, which is really, really ugly. But I think the key is that the only difference is that you map your coordinates, and then you subtract out this log of the Jacobian term. So the formula to do this is transform the sampled coordinates into new coordinates, evaluate the energy in this new configuration that you achieve by transformation, compute the Jacobian of that transformation at that point. This can be a spatially varying Jacobian. It does not have to be constant. Subtract that, because there's a free energy cost in shrinking or expanding the volume. Do everything else the same as standard reweighting. Plug it in. You can use the exact same codes to solve these equations. And then you can do things like, okay, what's the free energy difference of this dipole as I change the dipole length? It's a fairly large free energy difference because the dipole is changing quite a lot. So we just do simulations at the end state. If we don't do, and so what we're doing, it's a fluctuating system, but we map based on the equilibrium distance. You can see with mapping, you can get essentially 200 to 300 times more efficient in doing this. Or computing salvation free energy differences between water molecules. The direct approach might be to calculate, if you have N, you remove one water molecule with one force field, and then you remove another water molecule with the other force field and subtract those two numbers, which are quite noisy. But what you can do is just say, I'm going to map between the geometry of one water model to another water model, take the free energy difference of that process, and divide by n, because I've done it for n of these. And so it's straightforward. I'd say not so hard. I said straightforward before. Now I'm saying not so hard to do this. There's some linear algebra. And so for all the molecules, any energetic parameter is scaled linearly. And so what we get is the direct calculations, taking the difference between two free energy calculations. With the same amount of simulation time as this, cycle closure tech shows it works. But mapped, we essentially get exact answers with the same amount of simulation time, 300 times more efficient. You can even optimize water doing this. So this is something my former student did quite recently, sort of resurrecting this stuff from before, optimizing the simulation over not just one pressure and temperature, but over 0 to 5,000 bars. So in this process, he evaluated over 4,000 models, but once you started with 5 water models at about 500 temperature and pressure points, you actually didn't need to do any more simulation. It was just reevaluation of energies once you were doing the mapping as well. So with just a couple weeks, he was able to optimize. So here I'm looking at differences in density, in temperature and pressure here, along with the number of water models. This is what we came up with, that you had essentially no error in the density over this entire range, with negligible differences at ambient conditions in some of the energetic parameters. So there's enough. You can do this now. These sorts of tricks allow you to do things like that. So, for example, we can create phase overlap and compute between solids. Let's say a Lennard-Jones solid at 2 different temperatures. We transform just by scaling the particle distances in the box volume, reevaluate the energies in new coordinates, and here the red goes to orange and the blue goes to purple. What had essentially no overlap has much greater overlap, and you can use that to calculate phase diagrams. So where's the machine learning, right? This is the machine learning. Where is it? Trying to adapt this to the data science age. Well, the real application is things like Boltzmann generators and normalizing flows, where you learn the mapping between distributions. And one of your distributions is something you can generate samples from very cheaply. And you learn how to map that to the more complex stage. So there's been some really cool papers in the last 2 or 3 years on that. I don't know that any of them are actually practical to use, but things are moving really, yes, we can do Fringer calculations, only implicit solvent, sorry. But I think there's a lot of room for things to grow here. So yeah, things I admitted. What are optimal paths between endpoints? We've learned a lot about that. Look at papers by Pham and Naden over this 4-year period. I think the problem is essentially solved. If you talk to us, I can not necessarily implement it in code well to do, but there's a lot of cool things there. What's the statistically optimal way to calculate free energy surfaces with reweighting without histograms? So that's something that's fun too. What we're working on now, things like, can we make MBAR solutions more robust and cheaper? How can you do it sparsely without so many energy evaluations? What about incorporating this or non-equilibrium versions into more adaptive calculations? And so, Weitze, one of my graduate students, has a poster here. I want to plug LiveComms, Living Journal of Computational Molecular Science. So this is a journal for papers that can and should be updated. And for the relevance of the people here, some reviews that have appeared on best practices with many of the authors in the audience, and enhanced sampling techniques, I think, are very relevant. And the key is, go read this. If you disagree, log issues in the GitHub, and we'll update it in the next version. So I'd encourage you to try contributing to these. I think there's some grand challenges here that we're really excited to work on. I won't go over. I'm about out of time now. Can we get reliable absolute delta Gs? Most of the industrial work is relative, but we really should be able to do this. Can we get flexible ligands, like the site of peptide mimetics, that would actually go in and fit in those protein-protein surfaces? There's got to be ways to do this. Can we sample multi-chemically on the space of many ligand mutants? And we'll hear a talk. We'll talk about that tomorrow and some cool things that have been done on that. And with machine learning, I think these are the big challenges. Can we learn maps directly between different ligands with sufficient accuracy, skipping alchemical medians? I think alchemical intermediates. There's ways to do this. I'm sure we can figure it out. Can we learn the ensemble of binding to a given target with accurate delta Gs by using these mapping approaches? So I've written for grants for some of these. None of them are being funded yet, but I think we can work this all out. So thanks so much.
Thank you very much. I know we may have time for one question. I don't know if we want to keep on time or, yeah. Do we have some questions for Michael?
While we're transferring.
Yeah. I'll ask then, so 10 years time with everyone's back here, what are we going to be doing then? Is it the same kinds of systems we're working on now, but more accurate, or
I don't know.
Bigger systems, more complex changes?
Predictions are hard, especially about the future. So I don't know. I mean, I think it'll depend where the effort goes. I think all of these things could happen in 10 years' time, but it could be that there's other things that people want to spend. It's really hard to tell. I think these are all things that could be done and then be fun to do, and we'll see.
Let's thank Michael again.